This is lecture 2 on the big picture of financial math for actuarial science. We're going to be talking about valuation of annuities in this lecture, various kinds of annuities. We'll talk about what an annuity is for the, also level, varying, discrete, and continuous annuities. Before I get into the main content of the lecture, I want to clean up some loose ends from lecture 1. One thing I want to do is I want to show you a couple graphs. I want to graph some fundamental financial functions, 1 plus I to the t and v to the t, which is the same as 1 plus I to the negative t, where I is the effective periodic interest rate, often an effective annual interest rate, and v is the effective discount factor. Just want to emphasize a few things about this graph. I'm making this in Mathematica so I can change the interest rate. Let's increase the interest rate a bit. The red graph is your accumulation function. A of t is 1 plus I to the t, and the blue graph is its reciprocal, v to the t. Most obvious thing to note here is that the red graph is increasing, the blue graph is decreasing. How should you think about that financially speaking? Well, the fact that the red graph is increasing means in the context of compound interest, when I is positive, that as time goes by, your future value, your cumulative value increases. And it's concave up. It's increasing at a faster and faster rate. Okay, that's a pretty intuitive thing, hopefully, to you. Maybe what's a little less intuitive is interpreting v to the t. That's a decreasing function of time. What does that mean? Well, remember, really, the present value idea was thought of initially this way. You want to take some value, like 1, and in this case, you want to think of it as a value of 1 at some point in the future, and pull it back in time to the present, find its present value. The further in the future that payment of 1 is, the lower its present value will be. How do you interpret the meaning of that? You interpret it this way. If that amount of money, say 1, is further in the future, you need less money now to deposit to grow to that amount of 1 in the future, the further that it is in the future. That's why this function is decreasing. 2 years in the future, if you are taking that value of 1 to be 2 years in the future, you might need about 0.8 right now to deposit at an interest rate of 10.54% to grow to 1 2 years in the future. Further into the future, like 10 years in the future, you've got that payment of 1 10 years in the future. What's its present value? It's perhaps around 0.4 or so. That's what you need to deposit now to grow to 1 10 years in the future. You need to deposit less because it's got more time to grow. Another thing is what I already showed you. As you increase the interest rate, the red graph goes up faster and faster, and the blue graph goes down faster and faster. That should make intuitive sense. If your interest rate is greater, 20% interest rate here, your money's going to grow very fast, 20% growth per year, say. And the blue graph goes down faster and faster. To accumulate to 1 10 years from now, you can deposit less, like around 0.2, for example, to grow to 1 10 years in the future. This graph goes down faster and faster, the more that I increases. Okay? So that's one thing I wanted to kind of clean up. This is a perspective you should always have in your mind if you're thinking about financial quantities, compound interest, etc. Let's review some other things. Let's review some formulas and think about these formulas in the context of graphs as well. Recall these formulas. You can write the present value discount factor v either in terms of I or in terms of d. It's a linear function of d. It's not a linear function of I. You might wonder what's the relationship between these graphs. Here it is. The blue graph is v as a function of d, 1 minus d. It's got a slope of -1 and an intercept of 1. The red graph is v as a function of I. So for the blue graph, I'm thinking of the horizontal axis as representing the value of the discount rate, d. And for the red graph, I'm thinking the horizontal axis as representing the interest rate, I. Typically, I and d are both close to 0. So most commonly, we're thinking about these graphs in this context. What else can you note here? You can note that the red graph is always above the blue graph. What does that mean? That means for a given value of I or D, say 10% for example, the corresponding value of v is higher when I is 10% than when d is 10%. By the way, if I is 10%, d will not be 10%. We'll look at a graph that emphasizes that in a second here. If I or d is 20%, same thing happens. The corresponding value of the discount factor v is higher when I is 20% than when d is 20%. You might wonder, what do I have here? What I have here is called an infinite series. It's actually a geometric series, a special kind of infinite series. It actually does equal this quantity as long as I is less than 1 here, which we are taking it to be. It's between 0 and 1. D and I have a nice relationship between them. Recall that D, the discount rate, was defined to be, for, say, an investment of 1, the amount of interest that you got during that year, say, divided by the ending amount. D was I over I plus 1. You can solve that equation for I as a function of D. You can find the inverse function of this thing, and you get this equation. And as usual, hopefully you recall that inverse functions, if you graph them both on the same set of axes with the same axis representing their independent variables, they are reflections of each other across this line with a slope of 1 through the origin. This is I as a function of d here. This is d as a function of I. I also have these infinite series representations of these things. Although, once again, they are only valid between 0 and 1 for the input. So actually this quality is not true when the graph is over here, but it is true over here. And again, like usual, mostly we're concerned about values of I and d that are relatively close to 0, so we're mostly concerned about what happens in here. Okay? So it's kind of interesting again to think about both functions increase. As d increases, I increases. As I increases, d increases. This one's concave up, whereas this one's concave down. That's a difference between them. For a given increase in d, I will increase faster and faster as d gets bigger and bigger. For a given increase in I, d will increase more slowly as I continues to increase. Would be how you can interpret those things. If you know about geometric series, which we will talk about more in this video, you can verify these equations. You can also think of these in terms of Taylor series if you know about Taylor series, which you should. More loose ends. Finally, recall that since v is 1 over 1 plus I, taking the reciprocal of both sides of that equation, 1 plus I is 1 over v, so I is 1 over v minus 1. Which can simplify to 1 over v quantity over v. So you can write I as a function of v, and you can interpret the graph of that too. The graph looks like this. The most relevant part in typical applications is right here when v is just barely less than 1 and I is close to 0. But you can graph it really for all values of v. What's going on when v is small, like say 0.2? If v was 0.2, this would be 1 minus 0.2 is 0.8. Divided by 0.2 would be 4. I would be 4, representing 400% growth. I would be fairly big. 400% growth means you are quintupling in size in a given period of time. Money growing, for example, from 100 to 500 would represent 400% growth. V would be 0.2. The discount factor would be 0.2 if you've gotten them out like 500 and you discount it back in time. By 1 year in that situation, you'd multiply it by 0.2 and get 100. But again, most typically what you're looking at is values in here. Can I be negative and v be bigger than 1? Yes, it can actually, if your money's not growing but decreasing instead. Then the interest rate would be negative and v, the discount factor, would be bigger than 1, which means when you pull something back in time, it actually gets bigger in the situation where the interest rate is negative. You can write this as in a series as well. Here's what it equals. This is valid when v is between 0 and 2, it turns out. But this series representation is true then. Okay, so these are good things to think about. Okay, not something you necessarily think about when you're solving problems, but to get the big picture of things, you should think about these kinds of equations and graphs. All right, let's get on to new content now. The first thing in this new content is this fundamental idea of a geometric series, both a finite geometric series and an infinite geometric series. You should be warned, sometimes mathematicians, when they say the word series, they automatically mean infinite. I will try to emphasize when something is a finite geometric series by putting the word finite in there. Here's the formula for the sum of a finite geometric series. Okay, you want to get really, really familiar with this formula. This is the most commonly used formula. Technically, when it's a finite geometric series, it's not calculus yet. But when we let n go to infinity, calculus comes into play. We take a limit of it. And we get the formula for an infinite geometric series. Those are the things you want to be most familiar with. Here's a formal way to write it in summation notation. You're adding terms of the form a times x to the k power, where k goes from 0 to n minus 1. If you write that out without the summation form, it looks like this. We take x to the 0 power to equal 1. Technicality is 0 to the 0 power is actually undefined, but we don't worry about that. We just take, formally speaking, x to the 0 power to represent the number 1. So this first term is really a times x to the 0 power plus a times x to the first plus a times x squared, etc. The last power of x is the n minus first power. Since we're starting with the 0th power of x, there are n terms in this sum. And what does it equal? As long as x is not 1, it equals this expression. Okay, this is something you want to memorize. You can also write it this way if you reverse the quantities on both the top and the bottom. This is definitely something to remember. If you've never seen it before, you're going to want to work on remembering it. You can write it this way, but there's actually a better way to think about it in words. A is called the first term of the geometric series here, the finite geometric series. It's this thing. A represents the first term. These two things match in this formula. X, sometimes called R, is called the common ratio. It's the thing you need to multiply each term by to get the next term. We need to multiply a by x to get a times x. We need to multiply ax by x to get ax squared. We need to multiply ax squared by x to get ax cubed, etc. You can also think of it as take any term but the first one and divide it by the preceding term. You get this common ratio x. That goes here and here in this formula. And we raise it to the power equal to the number of terms. There's n terms in this case. I think this is the best way to remember it. That's going to help you handle situations where it's maybe not so obvious what a or x are. Or maybe in situations where if you write it in summation form, k doesn't start at 0. This can still help you think it through and get the right answer. How about an infinite geometric series? As long as it's convergent, it converges to a over 1 minus x, which is the same as the first term over 1 minus the common ratio. When will that be true? It's true as long as the common ratio in absolute value is less than 1. Between -1 and +1, exclusive, do not include 1 or -1 in that. This is a strict inequality, that is important. Most of our applications, x is going to be between 0 and 1. All right, that's the formula for the sum of a convergent infinite geometric series. If this is not true, then the series diverges. It doesn't make any sense to talk about the infinite geometric series except as a purely symbolic thing if you feel like it. Actually, the purely symbolic thing actually does have some applications, but not for us. Our main topic for Chapter 2 is to talk about annuities. We want to apply the formula for geometric series to annuities. What are annuities? An annuity is just a sequence of payments. I say sequence kind of loosely. It could be a finite number of payments. It could be an infinite number of payments. It actually could be a stream of payments, a continuous stream. It's also sometimes called a cash flow or a stream of payments, or deposits, or withdrawals, or benefits, or premiums. These last couple words, benefits and premiums, refer to insurance applications. You pay a premium to the insurance company and they give you benefits when you need them. Annuities can be level or constant, or they can vary. They can be discrete or continuous. Discrete would include finitely many payments, not phi, but finitely many. It can include countably infinitely many payments, like one, then the next, then the next, then the next. Or they can be what's called continuous, where you imagine money flowing constantly every second, every millisecond. It's a continuous model. The payments of a discrete annuity are commonly equally spaced in time, but they don't have to be. The payments can start right away, or they can be deferred, maybe by 1 year or 2 years, for example, before you get your first payment. Annuities may or may not have a clear pattern to their payments. The ones that do have patterns are the easiest to analyze and assess and value. And you can value annuities at any point in time according to some interest rate model, though the most common things are right away, time zero, or some fixed time at the end of the payments, if there is an end. Okay, so this is the main idea of Chapter 2 that we're going to analyze now. What's the simplest kind of annuity? We do spend a lot of time with relatively simple annuities, and then we sort of try to combine the relatively simple annuities in certain ways to deal with more complicated situations. The most simple kind of level annuity would be when you've got end payments of, say, $1, €1, whatever, spaced out by one period, often 1 year. You can visualize it this way on a timeline. Remember I said in lecture 1 that timelines are a really important problem-solving tool. When I solve actuarial problems related to financial math, I'm almost always drawing a timeline. And again, if you look at the problem-solving videos that I make, you'll see in watching those that I make lots of timelines. So here is your timeline with your times, time 0, time 1, time 2, time 3, etc. through time n. N is often an integer, but doesn't necessarily have to be, though almost always in this kind of setup it is. And then you've got these payments of 1, then 1, then 1, etc. 1, n payments of 1 at those moments in time. We call this kind of annuity an annuity-immediate if the accumulated or future value is evaluated immediately after the last payment. And as far as I can tell, that's the origin of the word immediate. The future value is evaluated immediately after that last payment, an instant after you make it. Okay? It's often phrased as occurring at the end of the period or the end of the year, your payments. It's actually not the absolute best way to think of it in general, but the best way to think of it is you're evaluating the future value of this stream of money here immediately after that last payment, and the present value of the stream here is evaluated not immediately before the first payment, but in fact 1 period before the first payment at time 0. Okay? But it really is, the labeling of the time is not so important as when you are evaluating the value of the annuity. And I say that here. The key thing is when the values are determined with respect to the last and first payments, not whether they are at the end of the period or the beginning of the period, though they are often thought of this way. When you are having this kind of timeline, oftentimes you are imagining these periods to be, say, years, and these payments to be at the end of each year. You call that annuity immediate. But again, the more important thing is you're evaluating future value immediately after that last payment, 1 instant after it, and the present value 1 period before. You can also think of such a level annuity in a different way as what's called an annuity-due. And I purposely made the timeline in this situation the exact same as before, even though for annuities-due, it's typically made differently. The key thing here, again, is not what the times are, other than the fact that you've got n periods that are equally spaced. The key thing is when are you evaluating the future and present values. If you evaluate the future value of this thing 1 period after the last payment, are we doing as far as how to see this? Does it look okay?
No.
Looks good? Okay.
It's got a bit of a glare.
If you evaluate the future value of this thing 1 period after the last payment, then you call it an annuity-due. Likewise, if you evaluate the present value of this thing right before, I'm going to avoid using the word immediate, right before the first payment at this time, then it's also called an annuity-due. So I purposely drew it differently than the way it's usually drawn. It's usually drawn in the following way. Take the first payment to be at time 0 at the beginning of each period, second payment at time 1, third payment at time 2, etc., last payment at time n minus 1. That's the way it's usually drawn when you say, okay, the payments are at the beginning of the periods. For an annuity due, we evaluate the present value at time 0 and the future value at time n. But again, the time labeling really doesn't matter. Okay, what's most important is when you evaluate the value of this thing with respect to the first and last payments. This is the more typical way to write it for an annuity due. But more importantly, even if you write it this way, you can still think of it as an annuity due. You're just evaluating the future value at time n plus 1 and the present value at time 1 if you draw it this way. How do you find the future value and the present value? Okay. Well, you need to add up the future and or present values of the individual payments. As an annuity immediate, for the future value, remember for an annuity immediate, you're evaluating the future value immediately after the last payment. These ones down here are all the payments, there's n of them. So I'm evaluating the future value. First of all, for this last payment, it's just itself because it's not moving in time. The payment of 1 at time n minus 1 needs to be promoted, pushed forward, if you will, in time by 1 period, 1 year, and its future value is 1 plus I. The payment of 1 at time n minus 2 would be pushed forward 2 years. Its future value would be 1 plus I squared. This payment at time 3 needs to go forward n minus 3 periods, 40 years, whatever. 1 plus I to the n minus 3. This goes forward n minus 2 years. This goes forward n minus 1 year. 1 plus I to the n minus 1. Commonly saying years, sometimes periods. It doesn't matter. It depends on the application. What do you get when you add those things up? You get a geometric series, a finite geometric series. This one corresponds to that one. This 1 plus I, which is this one pushed forward by 1 year, corresponds to this 1 plus I. There's a 1 plus I squared that comes from the payment of 1 at time n minus 2. Right there, etc. 1 plus I to the n minus 1 is the future value of the first payment at time n. And that is a geometric series. Thinking about that word form of the closed formula, its sum is the first term, 1, right there, times in parentheses 1 minus the common ratio. What do you need to multiply each term by to get the next term? You need to multiply it by 1 plus I. The common ratio is 1 plus I, so we have 1 minus 1 plus I. We're not doing an infinite geometric series here, so it doesn't matter that that's bigger than 1. This is a finite geometric series. To the number of terms power, there are n terms here. We're starting off with a 1 plus I to the 0 power. There's n terms there. Divided by 1 minus the common ratio. And this does simplify. These ones cancel. You're left with a negative I on the bottom. And you've got a 1 minus this thing on top. You can get rid of the negative 1 and switch around the order on top to get this. Multiply the top and the bottom by negative 1 effectively. To get this formula, this is going to be a formula you're going to want to remember for the actuarial exam. You're also going to want to remember this symbol over here. Sn, with a bar kind of above the n and to the right of the n. Actually, when you write it by hand, and in many books it's typeset in the following way, where you sort of just make a upside down L without making any space between the lines, like you see a tiny little space right there. That's just an artifact of the way this PowerPoint was formatting equations. It didn't allow me to make sort of a continuous upside down L. Sometimes you'll also see an I put to the right of this thing to emphasize that the interest rate, the effective periodic interest rate is I. But oftentimes the I is not, you don't bother writing it there. And in this video for today, I'm not bothering to write it there. It is assumed there is some effective periodic interest rate I that's going on. When there's maybe two situations where you got two different interest rates, then it's important to put the interest rate label there. All right, so you're going to want to remember this formula and this symbol. What about as an annuity due? You're evaluating the future value 1 period after the last payment. So your income stream consists of these ones, not that thing. That's the last payment right there. You're evaluating the future value 1 period in the future, 1 period after the last payment, I should say. So you need to push all these quantities forward in time. This last payment goes forward by 1 period. The second to last goes forward by 2 periods. The first payment goes forward by n periods. 1 gets promoted to 1 plus I to the n. And once again, the future value is the sum of these things, and they form a geometric series. The future value at time n. Here I am writing the annuity due in the more typical way, starting at time 0. And thinking of these payments as being at the beginning of each period. Once again, a geometric series. You got the S symbol here with double dots above it for annuities due. Kind of weird. It doesn't have anything to do with derivatives. If you know about using dot notation for derivatives, this has nothing to do with that. Okay. I don't know why this notation was chosen. It is. It's the future value of a level annuity due with payments of 1 at the beginning of each period. So this is evaluated 1 period after the last payment. 1 plus I plus 1 plus I squared, etc. I'm adding up these things here that are stacked. It is a geometric series. First term is not 1 anymore, it's 1 plus I. So you see the 1 plus I there. Common ratio is still 1 plus I, so we still have a 1 minus 1 plus I to the number of terms power divided by 1 minus the common ratio. And this can be simplified to this form. You'll want to use the fact that D is I over 1 plus I, so 1 over D is 1 plus I over I, to simplify it to having a D on the bottom. It is a very nice coincidence, I think it's a coincidence, that due starts with D and immediate starts with I. The denominator when you're doing an annuity due is a D, the discount rate, and the denominator when you're doing an annuity immediate is an I, the interest rate. And yes, due starts with D and immediate starts with I, a very fortunate coincidence. That's one way to help you remember it. What about present values? Here's an annuity immediate. I'm evaluating it, most importantly, 1 period before the first payment. V is the discount factor. I have to pull these back in time. This first payment at time 1 goes back by 1 year. Its present value is V. Second payment at time 2 goes back by 2 years. Its present value is V squared, etc. The present value of the entire annuity is the sum of those, which is once again a geometric series. Instead of S, we use A. A sub n represents the present value of this level annuity immediate with payments of 1 that are equally spaced in time. We are evaluating the present value 1 period before the first payment. Remember, this could be written in terms of I, by the way. V is 1 over 1 plus I. So this could also be written as 1 plus I to the negative 1 power plus 1 plus I to the negative 2 power, etc. But we find it simplest to write it in terms of V. It's geometric. First term is V. Common ratio is V. So you get the first term times 1 minus the common ratio to the n power, where n is the number of terms, divided by 1 minus the common ratio. And it is also true that V over 1 minus V is the same as 1 over I, to simplify to this last form. And once again, we have an I there, and yeah, immediate starts with I. By the way, you would get the exact same answer if you switched around the order of these things and thought of that as the first term, V to the n, and thought of 1 over V as the common ratio, or V to the negative 1. Let's just verify that you get the same answer. The first term being V to the n, the common ratio being V to the negative 1, still n terms. You get this. This should simplify to the same thing. How can we make it look the same? We could probably multiply everything by V on the top and the bottom, and distribute the, distribute the V to the n through here. we get v times in parentheses v to the n minus 1. Over on the bottom we get a v minus 1, and you can switch around the order of these things and get the exact same expression that you see right here. So you can think about it either way. Same thing as that. All right, there's an annuity immediate, present value. What about an annuity due? Once again, we use an A for present value. Once again, we go back to using double dots for annuity due. Now the first payment, say, is at time 0, if you like. Evaluating the present value of this income stream right before the first payment at time 0. This one doesn't move. It is part of the income stream. It's also part of the summation. This one gets pulled back by 1 year. This one gets pulled back by 2 years, 2 periods. This one by n minus 1 periods. Add them up to get the present value. We use an A for the present value instead of an S. S is the future value. We use double dots because this is an annuity due. It's once again a geometric series. And once again, when you simplify it, you get a D on the bottom. And yeah, annuity due starts with D. Okay, so this is great. All right? These are formulas you are going to want to remember. As you practice problems, you're going to want to remember these formulas without having to look them up. We could be evaluating the present value maybe 3 or 4 or 5 years before the first payment. We could defer the first payment. What's a K period deferred annuity immediate? It would be when you're evaluating the present value of such an income stream, really K plus 1 periods before the first payment. So if I make the first payment be at time K plus 1, and the payments, there's n of them up to time K plus n, you can think of it as a 2-step process. First, find the present value of this thing as an annuity immediate 1 period before the first payment, so at time K. So this goes back by 1 year, this goes back by 2 years, or periods, this goes back by n periods. And then each of those payments needs to go back in time to time 0, back by k years, so I need to add k to all the exponents. It's a deferred period annuity. It's a K period deferred annuity immediate, because you're thinking of it as annuity immediate K periods after time 0. There's time K, the first payment is 1 period later. It's a K period deferred annuity immediate. If we started the payment at time K, we could think of it as a K period annuity due. Anyway, its present value can be thought of as taking the present value 1 period before the first payment at time K and multiplying that by v to the k. Or you can think of it as in terms of a finite geometric series. Either way you think about it, you get this thing for the final answer. There's another way to think about it that's kind of cool. You can also think of it as the difference of two annuities immediate present values. AK plus n minus AK. AK plus n would represent getting k plus n payments. And if we're evaluating at time 0, thinking of it as an annuity due immediate, we'd start the payments at time 1. So we have a payment of 1 at time 1, 2, 3, etc., k plus 1, k plus 2, and etc., up to k plus n. We'd have k plus n payments. Its present value at time 0 will be denoted by this symbol. And this one could be thought of as an annuity immediate starting at first payment at time 1 that's got k payments up through time k. Taking the difference of those two things gives you the present value of what's left over, so to speak. So it's almost like you're subtracting two timelines. You've got a timeline with, I'll write it above the same numbers here. You've got a timeline with k plus n payments. Timeline with k payments, starting at first payment at time 1. Subtract the bottom annuity from the top annuity, and you're left with the annuity that we started with. These cancel. Okay, they are at the same moments in time. It is valid to cancel those things. Formula-wise, if you use the formulas for those present values, you can pretty quickly see you get the same answer. Okay? You want to be flexible in your thinking. You want to be able to think about these things in all these different ways. Continuing, lots of formulas in this lecture here. Before we go on to other kinds of annuities, here's some identities, some equations you should know intuitively, without having to think about them very much, and without having to rederive them, though you should be able to if you're asked to. For example, these four equations. Sn is v times Sn double dot. Conversely, Sn double dot is 1 plus I times Sn. An is v times A double dot, and An double dot is 1 plus I times An. What's going on here? Let's take one of these as an example. If our annuity is n payments, say, starting at time 1, if we evaluate the future value of this as an annuity immediate, it would be evaluated at time n. If we evaluate the future value of it as an annuity due, it would be evaluated 1 period after the last payment at time n plus 1. And these are two numbers. This one's going to be a bit bigger than this one is. To get from this one to this one, I hope it makes sense that you just multiply by 1 plus I. You just promote this one quantity forward by 1 here. Multiply it by 1 plus I. There's a visual verification, a non-algebraic verification of this equation right here. Likewise, you can go back the other way with v. You can take that future value and pull it back in time by 1 period by multiplying by v. Same kind of idea with these things, with these present values. Some other equations, identities you should know without having to think about it much, involve relating future and present values. Take the present value and push it forward by n years by multiplying by 1 plus I to the n, you'll get the future value. Same kind of thing holds with these annuity-due quantities. Take the future value and pull it back by n years, you get the present value. Same with annuities-due. Okay? I would encourage you to verify some of these algebraically. It's not too hard. But you should just be able to think them through with timelines. It should become second nature to you. What's a perpetuity? That's how you pronounce that, perpetuity or perpetuities. They're annuities that go on forever, perpetually. As an annuity immediate, pretend these ones go on forever. So the first payment is time 1. We want to evaluate the present value at time 0, so it's an annuity immediate. Pull this one back in time by 1 year period, this by 2 periods, that by 3 periods, etc. forever. The present value at time 0 is going to be a geometric series that's infinite, goes on forever. It equals the first term, v in this case, divided by 1 minus the common ratio, which can be simplified to 1 over I. Notice that we put an infinity there in place of the n. And this is going to converge as long as v is, as it typically is, between 0 and 1. Okay, if v is bigger than 1, then it doesn't converge. Don't use this one. V is bigger than 1, it wouldn't converge anyway. And we don't find future values of perpetuities like this, okay? We only find present values. As an annuity due, formula simplifies ultimately to 1 over d. Again, fortunate coincidence, I is the first letter of immediate, d is the first letter of due. These formulas are very simple. That's very nice. How about a deferred perpetuity? I didn't put it on the screen here, but you should be able to do that. We're doing a k period perpetuity immediate. It would look like this. Go back in time by 1 period to k, and the present value is going to be a sub infinity, which is 1 over I. Go back another k periods to time 0, and you got to multiply it by v to the k. So you get v to the k over I. And you could do something similar for a.k.a. deferred, perpetuity due. Those are all level annuities. What about varying annuities? Your payments, for example, could be geometrically increasing, where the growth rate is R. And this is definitely something that happens in practice, because if you're getting the annuity when you're retired, for example, you want your payments to go up so you can keep up with inflation. So in the simplest case, we have a payment of 1 at time 1, a payment of 1 plus r at time 2, a payment of 1 plus r squared at time 3, etc., through a payment of 1 plus r to the n minus 1 at time n. We're wanting to find the future and present values of these things, all put together. You could draw a timeline, but I won't bother. The present value at time 0, we need to multiply that payment by v, this one by v squared, this one by v cubed, etc. There's the pattern. That's a finite geometric series. First term is v, common ratio is v times 1 plus r. First term times 1 minus the common ratio to the n power, where n is the number of terms. You see n is the number. Divided by 1 minus the common ratio. You can simplify to this. How multiply the top and the bottom by 1 plus I would be how to go from here to here. If you multiply this by 1 plus I, it cancels with the v. And you're left with this, which is the same as this. This thing right here, since v is 1 over 1 plus I, is the same as this. Multiply the bottom by 1 plus I, it cancels there with the v. You get a 1 plus I here. 1 plus I minus, in parentheses, 1 plus r. The 1's will cancel. You'll be left with I minus r. What is the future value at time n? Once again, you can draw a timeline. You can push the first payment of 1 forward by n minus 1 periods to get this future value for that first payment. Push the second payment of 1 plus r forward by n minus 2 periods to get this for the future value, etc. This is, again, a finite geometric series. It simplifies to this thing. And do note also that you can derive the second equation from the first. The future value is 1 plus I to the n times the present value. If you multiply this by 1 plus I to the n, you get 1 plus I to the n there. You get cancellation in the second term. The bottom stays the same. You get this formula. So once again, you should be flexible when you're thinking about how to derive these formulas. This is a very formula-oriented lecture. We're going to keep going with formulas. How about an arithmetically increasing annuity immediate, which is actually a more common thing to think about? Suppose the payment is 1 at time 1, 2 at time 2, 3 at time 3 in general, n at time n. What's the present value? Well, symbolically, it's denoted by this thing. The I stands for increasing. It's arithmetically increasing, going up by the same amount each time. There's not a common ratio, but instead a common difference. The A stands for present value. The N stands for n payments. The first payment at time 1 has a present value of v. The second payment of 2 at time 2 has a present value of 2v squared. Third payment of 3 at time 3 has a present value of 3v cubed. This is not a geometric series. However, through a bit of trickery, you can relate it to a geometric series. If you multiply both sides by v and subtract the resulting equation from the original, I'll let you check that you get this. You can then divide both sides by 1 minus v, and then use the fact that 1 minus v equals d to get this thing. Also using the fact that this sum is an. You should recognize that too. It's more common to now multiply the top and the bottom of this by 1 plus I to write it this way. It is more common to write it that way, though I will warn you, in either situation, either way you write it, even though this is annuity immediate, the formula still involves something related to annuities-due. A D in this form of the formula and an A double dot in this form. So this is the more common form to use. It's a bit trickier then because of that, so watch out. Multiply both sides by 1 plus I to the n to find the future value. You see that down there? Which is denoted by IS. Increasing annuity, arithmetically. S is the future value, n payments. It simplifies to either one of these things. All right, all these things I think in general are worth memorizing, or at least remembering some of them and being able to do tricks like multiplying by this to find the other ones. Okay, so if you're writing these things down, make sure you work on trying to remember them if you're going to take the exam. There's an arithmetically decreasing annuity immediate, a payment of time n at time 1, n minus 1 at time 2, they're going down, n minus 2 at time 3, all the way down to a payment of 1 at time n. You can draw a number line for this. What's the present value of this at time 0 as an annuity immediate? It's this summation. D stands for decreasing. Okay, this is a decreasing annuity immediate. It's arithmetically decreasing. It goes down by 1 each time. And as the summation, it equals this. That again is not geometric, but it's related to a geometric series once again through trickery. Multiply both sides by v and subtract the original equation from the result. In the previous slide, we subtracted the result from the original. You can write it like this. You can divide both sides by v minus 1 and multiply both sides by negative, top and bottom by negative 1. Remember that d is 1 minus v. To get either one of these equations, this is the more common way to write it, right there. To get from here to there, I multiplied the top and the bottom by 1 plus I. And you can find the future value by multiplying everything by 1 plus I bn. Okay? So again, lots of formulas here. You want to get some practice with these formulas. Start to try to remember them. You want to practice some problems, like in my problem-solving videos. Okay? These are definitely things to work on. Pause the video if you need to write everything down. I need to keep going here to keep my time not too long. We've done discrete annuities so far. What about continuous annuities? What about when it's a true payment stream or flow or cash flow? Money is flowing constantly into your bank account. Sounds great, huh? Well, what are we given? In the general situation, we're given some continuously paid payment stream, or for short, just continuous payment stream, h of t. This is a rate of payment. It's not an amount of payment. It's a rate of payment in dollars per year. So if at a certain moment in time the value of h of t is 1,000, then at that moment you are getting money at the rate of $1,000 per year, which would be a certain number of dollars per day, and etc. Okay? At that moment in time. But the next moment in time, so to speak, it could change. That rate of payment. And an accumulated amount function, a of t, based on some force of interest function, delta sub t. Sometimes the accumulated amount function is called just an accumulation function. Okay, we're going to think intuitively about present and future values. I'll draw a timeline here. So you've got a timeline. You've got the current time is time 0 and some future time at time n. And you've got the particular moment in time that you're thinking about, call it time t. And you're imagining a tiny amount of time going by. A second, a millisecond, whatever. Technically speaking, things like this, dt, are called infinitesimals. And we are sort of playing loose with infinitesimals. We're not being rigorous in thinking about them. Just imagining dt as representing any amount of time that goes by. Okay, it's from time t to time t plus delta t, t plus dt. This is not rigorous math here, what I'm doing. You can make infinitesimals rigorous, but we're not going there. The nominal amount paid over that tiny interval of time is the product, h of t times dt. H of t would be, say, in dollars per year, and dt would be in years. This product would be in dollars then. That's the nominal amount. It's in name only. It's not a present or future value. That's the amount at that moment, tiny interval of time that you get paid. The present value of that amount is found by pulling it back in time to the present, to time 0. Multiplying it by a of t to the negative 1 power, the reciprocal. Not the inverse function. This is the same as 1 over a of t. This is the same as h of t divided by a of t. And the future value, if n is past time t, is found by multiplying h of t dt by the ratio a of n divided by a of t, which can also be written this way. Those are the present and future values of these tiny amounts of payment here over this tiny interval of time. To find the total present value or future value of the entire income stream, you need to integrate to get these equations. Integrate this thing right here from 0 to n to find the present value of the entire income stream. That's what I got right there. Integrate this thing from time 0 to time n to get the future value of the payment stream. And do notice that the a of n can be factored out of the integral because it doesn't depend on t, and you can think of this as being a of n times the present value. I am assuming a of 0 is 1 here with what's typical with, excuse me, with accumulation functions. Are these integrals hard to do? Well, it depends. It depends on, what kind of formula a of t and h of t have. If h of t is constant or linear, these are not too bad. And also, if a of t is an exponential function, typically these integrals are not too bad. And we're going to see examples of that here in a second. You can write these things in terms of the force of interest. You recall from lecture 1 that in terms of a general force of interest that's not necessarily constant, your accumulation function is this thing, e to the integral of the force of interest from 0 to time t. I use a dummy variable here, tau. The variable for this function is that upper limit of the integral. And the discount factor, the reciprocal of the accumulation function, is e to the negative of that integral. Therefore, you can rewrite the present value, excuse me, from the previous slide like this. This thing is the same as a of t to the negative 1 power. Same thing as that. And the future value, like this. This is a of n. This is a of t to the negative 1 power. You can simplify it by subtracting the exponents and also using properties of integrals. That the integral from 0 to n minus the integral from 0 to t would be the same as the integral from t to n. So it can be simplified to that. Okay, so these are very general equations that can be used in a lot of circumstances. And I think at my cleanup of this lecture, in the next lecture, I think maybe I'll do some examples of these that are non-standard examples, oddball examples like I did in the first video. But in this one, let's do more simple situations, like a level continuous annuity, where you're getting money at a constant rate, and a constant force of interest. So I'm going to assume h of t is constant at $1 per year. Yeah, not very much money, but oh well. And you're getting it continuously. There's the force of interest. I'm pretending it's constant. It's going to be natural log of 1 plus the interest rate. The interval's from 0 to n. What's the present value? It simplifies to this thing here. And the symbol for it involves a bar. And what's the future value? No, we're not there yet. Oh, excuse me, no, we are there. Okay, future value is this. First, let's just think about how you go about verifying these by hand, and then let's notice that the answer involves similar kinds of patterns to what we've seen before. Doing this integral means you have to find the antiderivative of e to the negative delta t, which, if you think about it, is going to be this thing right here, negative e to the negative delta t divided by delta. If you don't believe that, differentiate this. You can think about it with a substitution if you like. You could let u equal either delta times t or negative delta times t. You've got to evaluate this from 0 to n. When you plug in n, the negative sign is still there, and you get this term. When you plug in 0, you're subtracting that term, so the two minuses cancel. E to the 0 is 1, so you end up with 1 over delta. That represents that part of the answer. And it's a very similar kind of thing. Remember the present value of an annuity immediate with n payments was 1 minus v to the n over I. And with annuity due, it was 1 minus v to the n over d. Here we get 1 minus v to the n over delta. a very similar pattern. The bar here again is for continuous annuity. You could sort of maybe think of that, the origin of that perhaps is because a line segment is a continuum. Future value is this. You can either do the integral or you can multiply this thing by 1 plus I to the n. You get the same answer either way. So these formulas are not too hard to remember. We essentially do the same thing we did with annuities-immediate and due, but instead of dividing by I or d, we divide by delta. How about if the function is increasing, linearly increasing, and in fact, having a graph that goes to the origin? What if this is our h of t? So now we keep getting money at faster and faster rates over time. You can look at these answers. You can also look at the symbols. It's an increasing annuity, increasing continuous annuity, therefore we have an I bar. It's a present value, therefore you have an A in there. Put the future value in the next slide. Do the integrals, get the answers. These would be harder to memorize, but perhaps still worth it. As far as doing the integrals, integration by parts would be necessary. You'd want to let u equal t and dv be e to the negative delta t dt. And either way you think about it, whether you to find the antiderivative or to write the integral as some term plus another integral, either way you think about it, you're using the same integration by parts formulas. This is the more common way to remember it, by the way, if you do want to try to remember it. Though, notice you got a and bar in there, so you'd also have to figure out 1 minus v to the n over delta to figure out what this is. Lots and lots of formulas. Got, I think, 3 more slides here. What about the future value? These are the formulas. This is the more common one to use. Notice the S's instead of A's. We are talking about future values here. Notice that we're not integrating t times e to the negative delta times t, but t times e to the positive delta times n minus t. We're pushing forward a small payment over a small interval of time to time n minus t periods in the future, and it's being promoted so we don't have a negative sign there in front of the delta. You should take the time to double check these formulas. I think also at the beginning of the next lecture we'll spend a little time thinking about these qualitatively, looking at some graphs. Almost done, hang on. One more example, decreasing annuity. H of t is n minus t, so that would be a linearly decreasing function, having value of n at time 0 and 0 at time n. Delta of t is still constant. Here are the present and future values. Oh, excuse me, just the present values. Once again, you should check these things. Once again, this one's the one that people use the most. Pause the video if you need to take some time to look these over and check these calculations. We're just after answers for the most part and just reminding you of what you would do. You'd use integration by parts here. You'd let u equal n minus t and dv be e to the negative delta t dt. Also notice the notation, d for decreasing annuity, bars for continuous, A's for present values, and the final slide we have S's for future values. Same situation, and you get these formulas. Okay? So take the time to look those over, rederive them, think about them. That's a summary of the main math content from chapter 2 of this book. There are a few things I skipped here and there. But you're not going to get good at this unless you do problems, okay? You've got to practice, you've got to put a lot of time into practicing this stuff. You know, hours and hours to get good at using these formulas, knowing when to use them, practicing, try to remember them so you can use them on the test, practicing your calculator usage, including some financial functions. For example, if you need to find unknown interest rates, you want to use some built-in financial functions. I've got a couple videos about that with my problem-solving set. I can think of video number 42 and video number 56, which I just made earlier today. where I used the financial calculator functions to help me solve some problems. So I hope this wasn't too dull looking at all these formulas. They are certainly useful in a lot of situations, and that'll be the end of this lecture.